So I'm Andreas Kollegger. I'm actually the current cloud wrangler of Neo4j. This is my good compatriot, Peter Neubauer. Peter?
Yeah, I'm one of the founders of Neo4j. We developed it back in the days in 2001, and now I'm doing mainly like community, engagement and getting people to love Neo4j.
And random acts of hacking.
And random acts of non-private production code hacking, basically.
Scheme of what's happening now with big data and the reaction of big data to, of NoSQL. Within the NoSQL space, we're a NoSQL database. And we're a graph database. We see the NoSQL space divided up in different kind of data modeling. Our data model is that we're a graph.
DB, which has some popularity, is a bit more sophisticated, and of course it's JSON structures inside, so it's sort of arbitrarily nested like the old-fashioned hierarchical databases, which would seem to encompass graph relations, wouldn't it?
It almost does. So actually, having started with key value that you mentioned, there's a nice kind of elaboration of data model from the very simple idea of key value store that, as you said, like, there's no structure whatsoever. There's very little, in fact, in a strict key value store. You have no idea what the value is. You just have a key, and you're going to get back whatever is attached to that. It's just a big hash map, right? That's one giant category, actually, within the NoSQL space. The categories that we see, that elaborate from there are from that simple key value store. If you add a little bit of knowledge about what's going on, you realize, okay, it's not just random, bunch of things we have. We actually have different categories of things. And we know a little bit about each of those categories. We have some expectation that, like, in this category, there might be a name property, or there might be a size property or something. That ends up being the column family. So that's your, your Cassandras and databases like that. Elaborating a little bit more, then you realize that, okay, instead of getting back just this one data record that has some optional fields, and that's nice, I actually want to have more than just a flat record. I'd like to have a little bit more saved as the value of each key. That ends up being a document database. A document database really just being a container of containers, or another way to look at it, of course, a container of containers, you just can also look at that as being a tree. That, if you elaborate a little bit more and realize, okay, if I have these isolated trees, but I want to maybe connect the trees to higher up in the branch, or I want to connect them to each other, that elaboration then ends up arriving at everyone's favorite NoSQL database category, the graph database size. And you could, in any of these models, you could be a graph. It could also just be a flat file system. You could use a graph to just be a flat table if that's all you wanted to do. But it's beyond just the model that each of these as databases are focused on particular use cases as well. So while you could use MongoDB, you could have relationships between the documents. If you actually want to do queries on that, if the questions you're asking are about those relationships, it's not very good at that. It's very good at like just getting collections of the documents. Not so good at, from this document, if you and I, if the three of us are documents, it's not so great at saying like, how do you, David, know Peter? That kind of a query is very difficult for it.
Yeah.
Whereas a graph database is optimized for doing those kinds of queries.
What
In this case, social ends up being very big, but then from that as well, you end up, once you kind of got the graph-like way of thinking, it's a very easy step to then realize that doing things like recommendations are incredibly natural to express within a graph query. If you're Amazon and like it's the classic, oh, you bought this book, people who bought this book also bought this other book, or bought this Cuisinart. Those kinds of relationships between the products and the people who bought them are such a graph problem. And in fact, like writing that kind of a query within a graph is just the most natural thing in the world. So social to recommendations, and then on to like things like network management is a huge area for us, master data management, doing logistics. A very classic thing, of course, as a graph problem is the seven bridges of Königsberg. I always get the city wrong. Königsberg. You say it in German.
Königsberg.
Good, yeah. The proper German of it. Yeah, that place. Routing
that was
and
formulated by Gauss, right? Is that right?
Yeah, I think it goes way back. Yeah.
That routing challenge, of course, is a graph problem, and that's a modern day problem if you're FedEx or if you're DHL or somebody, and that's your everyday problem is I've got a package, I've got to get it somewhere, coordinating how much you can fit into a truck. Very natural for using in graphs as well. And then once you start realizing this slight shift in perspective from a relational model to like the same kind of data can be modeled in a graph, but the kinds of questions you ask end up being different. And then you realize, oh, all the same data I already have is also graph data. It's just, instead of looking at it as just purely set data, you realize, oh, I can ask different questions. If I take my same domain, but just put it into a graph, the domain hasn't changed, but the questions and answers are different.
You suddenly have a product configuration for an airplane, that goes like in variants of ingoing parts and components down like 10, 12 levels, which means at the very least you have to require 10, 12 joins when pulling this out, which takes 10, 100 minutes.
Yeah.
And which in Neo4j is just a graph local query and takes like a few milliseconds.
Yeah.
So it's like it's the difference between modeling your many-to-many relationships as tables and linked tables and take that query hit when you need it, like in runtime, as opposed to modeling these things explicitly as relationships with direct pointers in the data model in the storage layer, and doing basically that work up front at insert time, and then at runtime have a constant time to ask these relationships. Most domain models tend to include cycles as soon as you not only have the tree with the variants, but even have like, and by the way, this comes from the same supplier.
Oh yeah.
I mean, every domain model turns into a big hairball if you look at it in reality.
Yeah. Well, I mean, certainly if I think of human social graphs, who knows whom and what relations? Obviously, there's cyclicities there.
Or things like
think of routers and networks and things.
Yeah.
Then obviously there's it's all about cyclicities.
Right.
But even pretty conservative structures like file systems, as soon as you have symlinks, you're back to a graph. So that's quite interesting. Things suddenly have more than one parent, and then you have a graph problem as soon as you want to do some analytics on that.
It's suddenly, the top is never the top. It's always, at the time I'm asking right now, what's my entry point into the data set? And then that shifts everything.
How do you?
So as a general solution, of course, partitioning a graph is an incredibly, at least mildly, fairly theoretically difficult problem to solve. We've done a lot of work looking at that as a general solution. And there isn't a good way to do it. There's not a good automated way without having some understanding of an application domain. You have to understand the usage patterns to actually be able to divide up a graph across lots of different machines and still have it perform very well for any kind of a query that might happen. Mm-hmm. It's possible to look at queries and then realize, oh, okay, actually based on what you're doing, let's move this over there, and that'll end up being faster, except the queries keep changing and that you're going to keep moving things, and any benefit you might have gained, you've lost by trying to move things around and doing the analysis. And so you have to have knowledge up front about how to divide things up, and that requires application level understanding.
Mm-hmm.
So one thing is that, as Andreas said, we have looked at what we call insert time sharding and runtime sharding. And runtime sharding is very costly. It's of course what everyone wants. You want to hotspot detect things that are much used, much changed, or whatever that might be, and change them around. But the algorithms to do that, like DDIX and others, are insanely expensive because you need to define fine global clustering in the graph based on like stuff, and that takes you weeks, and so the whole benefit is gone. By far, the most benefit is insert time sharding. Mm-hmm. But that's what basically the other NoSQL solutions are doing. They're forcing you to insert time shard your data. If you have a document database, then that is forcing you to cut between the documents and not expect any valid links between them, because if one document is going, the reference from these other is gone, and you have to deal with it. So because there is no guarantee.
There's no referential
What Neo4j does is to give you a guarantee. There's referential integrity between all nodes and their relationships. So there is a level of referential integrity, and we intend to keep it that way, even if the references get more expensive between shards. Mm-hmm. So now the interesting question is to expose a good way to slide not only whole of your data model, I have a totally document-oriented or a key value store, but just parts of your data model, because you might have like a small part of your graph that is like reference data, like all your users, and then you have another part of your graph that is shardable,